to talk about real gases as compared to ideal gases, because in the past couple videos that I've posted, I've been talking about the ideal gas law, which is PV equals nRT, or PIV-NERT. And what I've said is that we can only use PIV-NERT when we have specific characteristics of gases, and we actually have to make some assumptions about those gases in order to use the ideal gas law. We have to assume that the gas particles themselves, whether they're atoms or molecules, have no volume, which we know, isn't the case. They're tiny, but it's not that they have no volume. And the other thing that we have to assume is that they don't interact with each other in any sort of attractive or repulsive way. And again, that's more true for some molecules than others. So I want to focus then on, well, what does this look like then for non-ideal gases, or for conditions that make us more hesitant or reluctant to use the ideal gas law? So that's really what this video is about. So I want to talk about kind of larger molecules, which if they're larger, that means they're going to have more volume, which means that it's less easy to make that assumption that that volume is negligible. And they potentially have greater stickiness to each other, which would have to do with their polarity. If a molecule is polar, it has a net dipole, which means that one side of it is slightly positive and one side is slightly negative. If you have a couple of those molecules in vicinity to each other, then the slight negative on one and the slight positive on the other are going to be attracted to each other. We call those intermolecular forces, so a force of attraction between molecules, and again, due to the kind of polarity that we see, the net dipole. So these things do not behave as ideal gases, and also there's some conditions that come into play. We said that the ideal gas law works kind of at standard pressures, temperatures that are higher or in the middle kind of range, but that it doesn't work as well at low temperatures, because that starts to slow everything down, which causes more potential interactions with each other, or really high pressures for the same reason, because if you have high pressure that's pushing all these molecules closer together, that's going to cause them to interact more. So these are kind of non-ideal conditions. So that means that we can't really make the assumptions that the ideal gas law is based on, so it's no longer a good approximation. So what do? Well, we have to factor in, for these kind of non-ideal situations, a term that is going to account for that issue with the volume, the assumption about the volume, and the assumptions about the pressure. And that gets us into what is called van der Waals equation. Van der Waals might be a familiar term to you if you've studied some biology before, because van der Waals forces are forces of attraction between particles or molecules, and it's related to what we see here. So he did a lot of studies with interaction and attraction between particles, and his equation is what we use when we're talking about real gases. So the V in PV equals nRT for the ideal gas law is the volume of the container. We assume that the volume of the gas is equal to the volume of the container, and we're neglecting the volume of the individual particles. But really, in van der Waals situations, when we have these kind of non-ideal situations, we have to factor in this term that takes into account how many particles there are, and some constant that's related to that particular gas, whatever the identity is. So this NB term is the number of moles times a constant that is associated with that particular molecule, and this accounts for that difference in the volume of the particles. So this is our new term for volume. Now for pressure, we said those attractive and repulsive forces are going to have an impact. So in the PV equals nRT in an ideal sense, it changes to whatever the actual pressure is, and then we have this term that factors in kind of the area, the space that these particles take up, and the interactions between them based on how many there are, the N, and the volume of the container. So it's essentially a mole squared per liter squared, so that unit doesn't have a lot of physical significance, except to say that it's a factor that is taking into account kind of the interaction between neighboring particles. So the greater the number of moles, right, the more that this is going to impact the actual pressure here, or the smaller the container, then the more it's going to impact the pressure, because we're going to have a greater amount of particles there. The pressure is no longer going to just be the pressure that comes from the collisions with the sides of the walls of the container, as we saw in Pivnert, but now there's going to be this potential of interaction between neighboring particles, and that's kind of factored in by, again, N is the number of moles, V is the volume. A here, like B, is a constant that's associated with a particular gas. So A and B are kind of look-upable constants based on the identity of it. So you can find these in tables in places. They're very Googleable. They would be given to you in a problem, for example. So speaking of problems then, if we're going to put this into our PV equals nRT, right, if this is our normal PV from the ideal gas law in Pivnert, now we need to factor these in, then that gives us what we call van der Waals equation, which looks a little scarier than our normal Pivnert. But it's not that much scarier because the N is still the same. The N is the N is the N. It's how many moles of gas we have. But we just have to factor that in when we are playing around with these pressure and volume variables that we had to make assumptions about with the ideal gas law. And the V's are all the same too, right? The volume is still the volume of the container, but by how much is that impacting these variables is going to be slightly different. So we call this van der Waals equation. And again, A and B are these constants that are associated with a specific gas and its identity. So we can use this then to solve problems that look like this. Maybe I can still keep it on the top too. So the question is kind of, what is the pressure in atmospheres for 1 mole of ethane at standard temperature? So what do I know? I know that my N is equal to 1 mole. I'm at standard temperature, which means that I'm at 0 degrees Celsius, or 273.15. I have 1 mole of gas at standard temperature. So my volume here is going to be, based on Avogadro's law, 22.41 liters. And then my R, since I'm looking for pressure in atmospheres, is going to be 0.821 liter atmospheres per mole Kelvin. It's asking me to solve for pressure. That's my unknown there. And then what I'm missing from my van der Waals equation are my A and my B values. So I need to go and I look up ethane. So ethane is an organic molecule that is made up of 2 carbons. That's what the prefix eth means. So I look up ethane and I find that my A value for ethane is equal to 5.570 liters squared atmospheres per mole squared, and my B is equal to 0.6499 liters per mole. Now you'll note these units are wacky, and the units of course are going to help sort the math out. So when we plug these in here, you can see that they're going to divide out the units that they're multiplying with. So that'll all kind of sort itself out in the wash. So then when I plug and chug through here, so I'm rearranging my equation to solve for P. I'm going to assume that you can do some algebra steps with me here, so I'm going to abbreviate that and just kind of give you the take-home message. V minus NB. So I rearranged my equation and solved for P. Then when I plug in my values for everything else, right, because all I'm doing is just substituting in, then I end up with a pressure of 0.9927 atmospheres. And again, kind of run the numbers, check it for yourself, make sure that jives with what you're thinking. And the interesting thing to me then is saying, okay, well, that's all well and good. What does that mean physically? Well, let's compare this to what we'd have if we had PV equals nRT. If we were predicting this with PV equals nRT, with ideal gas law, then I have the volume, standard volume of 1 mole at the standard temperature. So what I would expect is that it would be at the standard pressure. Because Avogadro's law says that regardless of the identity of the gas, if you have 1 mole at standard temperature in this volume, then you would be at 1 atmosphere. Because standard temperature and pressure is 0 degrees Celsius, 1 atmosphere of pressure. So with ideal gas law, I would have predicted that I would have had 1, the actual 0.9927. Now, that may not be a very impressive difference. It becomes more of an issue when we start tweaking the volume of the container, when we start tweaking the temperatures of things, when we start looking at kind of less than standard conditions and maybe gases that have a few more interesting features about them. Ethane is non-polar, so it's not going to have a lot of stickiness between them. So these numbers are going to be different, slightly different than something like water vapor, for example, that would be a more polar substance, and that would have more of an impact on how it interacts with itself. So again, this doesn't look like a big, significant, striking difference. You can see, though, that there is a factor at play when we get larger molecules like ethane, which is C2H6, so it's a little bit bigger, has a little bit more of an impact. And just something to keep in mind, because we are always making assumptions with models, and it's important to be able to recognize what those assumptions are when we are making calculations, because it could have a big, more significant difference, kind of depending on what we're working with. So that's a little bit about real gases and van der Waals equation, and if you have any questions on this, don't hesitate to reach out. Otherwise, I will talk to you again soon.